Hello guys, welcome back to another episode of eBPF programming. In this programming part 5, we will be exploring network security with eBPF. And I have divided this eBPF network security into two parts. Part 1 will be exploring more on XDP, and the parts 2 I will be showing LSM hooks, how we can leverage LSM hooks in network security applications. And in this one, it is XDP, and what exactly it is express data path, and it's a kernel network programming technology used for fast processing, packet processing. That means it allows you to attach eBPF programs at the earliest possible point in packet reception. That means before it reaches the kernel stack, we can put a hook on the packet and we can process the packet, and we can place our logic on the packet, what to do with the packet. As I said, it operates at the driver level and processes packets at the lowest level of the network stack. Because it's not reaching the kernel stack, it doesn't need to allocate any memory for the packets. So in terms of performance, it will be high performance applications. And yeah, of course, we can put our own hook on the package, so programmability control will be more. And as I said, it triggered for every incoming packets, and you can make decisions on whether the packet needs to be dropped, passed, or redirect, or if you want to modify, you can modify the packet properties. And basically every XDP eBPF program will be by default it passes an XDP MD structure that represents the metadata of the received packet. So these are the members of the XDP MD data structure. So it has the actual data and the end of data. These two members are really important for us because we access the actual packet using these two members. Then there are some other things that I'm not using in this program, but if you seriously planning to develop some more stuffs, like suppose we are planning to develop a load balancer or some other DDoS mitigation stuff, so you may need to make use of this in these other fields like ingress index of the network interface and the egress index of the network interface. We will explore, and anyway we will be exploring everything one by one. For this first program, we'll be simply exploring how we can make use of the normal other members and how we can process a packet. And this is this picture is taken from the latest book for eBPF. Is called Learning eBPF. In that they explain this diagram like this, and as it shows the physical network connection, you can see the hook is placed on the NIC card itself. So from there we can put our eBPF program and we can process the packet, and we can take a decision on what to do on the packet before reaching the kernel stack. Means you can put block based on protocol level or IP level. You can decide what to do on the packet. It can be redirected, or it can be passed to a kernel stack, or it can be completely dropped off. There are a lot of XDP based enumerators that works on the packets based on our logic, that you can put hook on the entire packet. This is a packet header when it receives on the XDP area or the NIC card itself. So we are going to explore this Ethernet header and IP header for our own process, because we are going to develop an application that works like a firewall. It is going to be like an IP based block for the incoming packets. So basically this Ethernet header has the source and destination MAC ID, and you can see there are two protocol types defined. The first Ethernet header has a protocol type that's that value has normally it is IPv4 or 6 or ARP as a protocol. And if you come to the IP header, the protocol type will be like ICMP, UDP, or TCP. And if you go deeper into the exact structure of this IP header and Ethernet header, you'll come to know more about what are the other fields that you can do and access. I strongly recommend just go and check the Linux source code for this one, because it clearly explains the members and what are the things that you can do with all these stuffs. And this is the program flow of XDP. It arrives at the NIC and the XDP program is triggered when you have a hook, and the program accesses the packet via this XDP MD that I explained already, and the program makes a decision on what to do on the packet. These are the enumerators that we can implement based on the logic that we play on the packet. It can be passed to the kernel stack, or we can drop the packets entirely, or we can redirect the packet to somewhere else. I think two more are there. It's XDP aborted, I think. Yeah, one more is there, so I forgot to add that here. All these things are here in the Linux kernel itself, so yeah, it is here. See, these are the exact list. It's defined here, so you just come here and check all the things related to the XDP, whatever things. If you have doubt on the structure or anything, you just come here and reference this. This is really a good website. I already shown it on my first video, so please always refer before doing that programming, or even when you have some doubt while you're developing eBPF app, just refer this site. You will get almost every information related to the eBPF stack itself. So as I said, we can do all these stuffs on the return code. I completely missed out about XDP aborted return code. You can add that and just go and check the reference for that. It is nothing but I think it drops the packets with a reason or something. It's not like a normal XDP drop. So yeah, now we are going to check the code of developing a firewall, simple firewall using XDP. It is nothing but we are going to make a firewall using XDP and eBPF, and it is going to work on the network level. The packets, we are going to process the packet before reaching the kernel stack itself, network stack, so it will be faster and easy to plug in and easy to use. In fact, I mean, I don't say easy to use because it needs a lot of programming effort to develop this. Yeah, maybe on the application side, if it has if it has the required headers, definitely it's easy to use also. So this is a source code for, and I follow the same logic that I use for all my other LSM hooks here. Instead of LSM hooks, here we are going to use the XDP. See, it's this much simple. As I said, you have to add this section XDP, because then after adding this one eBPF, that just-in-time compiler is going to recognize this as an XDP part. I hope we know how the compilation process happens, because it's again that I explained already in my other videos. So because this one is not compiling to the actual machine code, instead it's doing a just-in-time compilation. So for that we need to follow the basic structure of eBPF. It should have, when a verifier is verifying this eBPF application, it checks for the license and which section needs to be added hooks. Like if you want to hook some other programming area like a kernel stack or LSM hooks, you need to mention that on the SC area here, just before on top of your method. So that kind of stuff I have already explained, so I'm not going to explain that. The same logic that we use for building the WAF and preventing the Linux local privilege escalation, I'm using the same logic. Previously we had the key as what to say, a string value that was used for checking whether the map has allowed or not allowed values in my previous application we developed. And here I'm using the same logic, but the key is unsigned 32 integer value, and the value is same. Value doesn't have any importance here because we are going to use the key as our IP that needs to be blocked. So how it works is just like the previous program. We create a map here and add that to the map section of the eBPF program, so we can access this into our user space application using the name of this map. So what happens here, whenever a packet receives, we are going to attach this to one of the interfaces in this Linux. So whenever a packet receives, this hook works and it comes here, and this structure will have the metadata for the packet, and we are going to going to process the packet using this method. So what exactly happens in this method, we just taking the data. Actually this has, as I already explained, this has the data and data end that shows the start and end of the packet, and we convert the data to the Ethernet header. Then we are just ensuring that Ethernet header is good enough to process. If it is not, so we just just put a pass on the packet, so it's not our headache to process. It's not the application head. This application is not going to process the packet if it is exceeding the data end. So if it is a good packet, then we are using another method called end host short. Actually this is another piece you have to be careful, and these are the things I learned newly in this XDP part. And this header is defined in this header. I mean, this function is defined in this header, bbfendian.h. If you are familiar with network programming, you already know the host byte order. I mean, the byte order of network packets. When we receive a packet, actually it is in network byte order. So if you want to process that packet normally, we have to convert that to a host byte order. So this function is doing the same. Like, it is converting that network byte order to host byte order and checking the Ethernet packets protocol type. So as I mentioned earlier, I don't know did you listen to that or not, the Ethernet header has here the Ethernet header has a source and destination MAC plus a protocol. So it checks here whether this protocol is an IPv4. Here I'm checking ETH IP, and if you have any doubt on this one, you can just even search here. You will get more details about this one, where it is defined. And see, it is defined here as a macro Ethernet ETH header, and see, this is defined here as an IP packet. So we are just exclusively checking for IPv4, and this is a value for that one, and that's why we just put a network to host short. It is short because it's 16-bit, and once this packet, if the packet has the IPv4 as protocol, then we convert that, take the data plus the size of the Ethernet header. That means we are just taking the data, entire data from the packet, including the IPv header. Like the process, when it comes to processing, it will be like you'll be taking data from here to the IPv header. So where is that? We take that and we check the condition that is not exceeding again, it doesn't go beyond the data end, and if it is within the data end that we can process the data packet. So we are fetching the IP header source address, and here is another important part you have to check. Here the source address is always on the network byte order. We are not converting anything here, we are just directly taking the network byte order, and is going to be an integer value like unsigned in U32 here. And I'm checking that direct source IP in network byte order inside my map, and if it is there, if it is found any IP that needs to be blocked, I'm just checking it, and this will have, if it has any value, this will be a valid one, then we block the IP and we return XDP drop from here to the actual function that we the XDP underscore FW. So the result will be returned here, and we return the action from here. Even directly we can return without any assignment of action variable, but just for clarity I just did that. So that's it. Actually it's the same logic that I use for the WAF and the Linux privilege escalation programs. And what happens on the user space application, there are some differences, it is not like a normal loader that I can show you here. So up to here it is same, like we are opening it and we are loading the skeleton file. One more important thing I forgot to mention is here I'm not using the VM Linux header. Instead I use the direct BPF header, because when I was dumping the VM Linux header, I was missing some constants like these, and it was pretty, I just got stuck on that part, and the solution was to redefine this constant inside your application using some macros, but instead I tried to use a BPF header itself. So the other thing is, like, if you want to use this header, you may need to add other related headers, because these two headers have all other necessary functions that we use, the structures we use, like IP header and Ethernet header. Then these constants all are defined in these two headers. We can try the same thing with VM Linux header, but the only thing is we may need to redefine the missing part inside the eBPF itself. So I just avoided that and directly use the BPF header. So it's really difficult to say sometimes. So we don't need to add the VM Linux header with extra definitions of these missing parts. So that's a part of just come to this point. We normally, just like the other application previously we did, we open it and we load it, but after this we have to do some extra work for this one. The first thing is we have to get a file description for the XD program. So the program name is this one, and this is the actual name that we use here, this one. And after getting the file description, we use an BPF XDP attach method, and that has these 4 parameters. And the first one is the index of the interface, that I am using this function if name to index with the interface name, and this function is defined, I think it was in yeah, I think this header, if I remember, I think that was a header. So I cut it and save it. Where was that? Oh, it's better we go. I just added all these headers when it was showing errors. I think maybe on, yeah, I think this one. Oh, sorry, the network interface header. If you see, if you remove it, it will show this one. So this one was defined here. So we need to add that header to get this method. We need this method because we have to get the index of the interface to add to this eBPF XDP attach method, pass the index and the program description. Then these parameters are we can pass it as null. If you want to know more about this method, you can come here and just search here. It shows the exact parameters. See the index and program description, and there's a flag. I just passed it 0 and it worked. I haven't checked for the other options, and this one I didn't do. For this application, it's a very simple application, so I'm not giving any XDP attachment options. I'm directly attaching to my interface, so I didn't give any other options. Just passed as a null there, so it's not a mandatory variable then. So yeah, this is a new thing that I learned when I was learning this XDP part, especially when you want to load this eBPF XDP attach. I mean, it's like a normal a custom user level application that loads your XDP to the interface. So that's a new thing. We need a program description file, program file descriptor, and you need to find out the index of the interface. Then yeah, that's the main things that you need to attach your XDP to the interface that you want to. Then all other normal thing that we already did. We are accessing the map description, map file description from the skeleton file, and once we get that, we add our blocked IPs. The IPs needs to be blocked for the incoming packets to the list, and we are adding that, updating our map here. That's it from this one. Apart from that, everything is same as the LS. I mean the WAF and Linux Pro escalation module we did already. Same thing, only two different new things. One is BPF XDP attach method, and other one is getting the index of the network interface. That's it for this one. Let us compile and try to run this firewall application. So here just make sure that I don't just deleting this one. So our firewall application is ready. Now we need to let me delete this things. I'm going to create the header again. That's why I deleted that, and there is no need of this one also. We will create it again. So make skeleton. Now we have the skeleton file from eBPF object. So the next thing is you have to create and run our loader application. So for that, I already set up here my Mac. It is loaded with these two IPs. The block hook is in action. So the another part here you have to listen is I'm just blocking it. I'm not taking any data from any other details from the eBPF application that is running. If you want to do that, you have to pass either using ring buffer or the other performance related arrays, perf related arrays to send data to the user space. And just because of that reason, I'm not running this application in a loop. It is just listening for a character to just escape. So here we'll be watching this one. This will be from the previous one, I think. Yeah. So application is running. Oh, before, okay. I think before the hook, let me try. I think I need to delete this. Once we attach this one, we have to detach that one. The detachment actually I'm not doing using inside the app. There is another method for detachment. You can use that. Yeah, I had to change that in that way. So once I'm just showing what happens before and after the firewall in place. So now there is no firewall hook. So when I'm going to do a ping, I'm getting the data from my destination. That means this is my Linux machine where the XDP application hook is going to be placed, and I will do another nmap, and I'm receiving all the values. I'm just the port states. So now this is we are going to place the hook. Now the hook is in place, and I'm going to watch this here. And it is always recommended if you place something using the map description from the eBPF app, you can view the map here using the eBPF tool map list, and from there you can see the map ID is 67 here, so you can watch the exact values whether it is updated or not, because here I'm printing directly from the array that I've already passed to the map. This is not exactly from the map I'm printing, but here you can see the exact values. And another thing, I forgot to mention that I already told on that this one, when we look up the map lookup is done directly using the network byte order. We are not processing we are not converting anything this to any host byte order. So when you are creating the IP blocks, the IP list, you have to keep the same thing, like it should be the network byte order. So this is a function that helps us to do that. We just pass the type of this is basically for IPv4, and these are the parameters for this function. This one is just converting this string. It should be a valid string, otherwise that's why I put an error. I check an error here. If it is not a valid string, this will generate this error. Otherwise this key will have the exact network byte order of these strings. So this should be, if you are processing something here, then you have to do the same changes here before looking up the map. So it's better not to change any network byte order when you are creating and when you are doing the map lookup. So yeah, now let us come to this. We have the map updated here. We already, it's working because it's getting, the network interface card is getting data and it's processing, but is this information is not coming from the blocked IP. My blocked IP is this one, this is one of the blocked IP, is 192.168.158 that I put here in my user space app to block. So I'm going to send, now as I shown you previously, before the hook I was getting the data information for the ping and the nmap. Now I'm going to do it again, starting with the ping. See, it says blocked IP detected, and here we are returning, we are doing a drop of the packet here, because if we are getting a blocked IP inside this one, we say XDP drop, that means a packet is dropped, is not going to send to the kernel for processing. And you can see this one, in fact it gets stuck here, you don't receive any data here, like, because it's completely dropping off the packets. So now it's a ICMP level. Even another thing that you can do is you can check the protocol on the packet, and you can combine these rules, like you can check with the protocol and add on IP. So that means like IP plus on the protocol check. Suppose if you want to just completely block only the ICMP packet, you can do completely on the packet, the protocol Ethernet header, not on Ethernet header, it's inside the IPv header, IP header protocol, you can check and block it, or you can combine these two rules. If you want to block from specific IP, you just say no one from that IP should ping to your machine, then you can combine this rule, IP plus the protocol. So the next thing I'm going to check is at nmap. So what happens before the hook plays, we got the result like this. So now the hook is there and it's going to block it. See, now nmap says the host seems down, because we are dropping the packets, we are not allowing any processing on the packets. It's not going to the kernel stack and returning anything back to the host machine, so we can completely block it. This is the simplest firewall thing that we can develop with this one, and this is just a normal thing. And if you search for the code, you can see different types of code on different versions. When I was searching for Rust, everyone was showing this in Rust, so that's the reason I just tried to convert that to, not converting, actually Rust is doing in a different way, and is far harder than C, I feel. This one is very straightforward. I can maybe if I'm going to be more familiar, because I stopped Rust programming I didn't touch Rust programming for at least for the last 1 year, so it feels again weird for me, all the keywords and all the syntax in Rust. But yeah, definitely I'm planning to use either Rust or go for this one, especially on user space, because on threading level, I think that those will be more efficient than this kind of C programming. This one is a single threaded, simple application, doesn't need to be so much complicated in threading. That's why I just loaded this application using the C itself. But going forward, I'll move my user space applications either to Go or Rust. The best part of Rust is like if you can develop both sides on Rust. But even if you use Go, till now what I'm seeing is like the eBPF app should be in C itself. but you can create more control loader application, user space applications in Golang. So that's it for this one. This is our simplest, the most simple firewall module for blocking incoming packets. And another thing I have to mention is, yeah, definitely this is one of the technology stack that most of the big companies are using nowadays. I think Cisco has invested a lot on eBPF and programming stuff, and I read somewhere that Cloudflare is using XDP eBPF in their DDoS mitigation. And those are the other areas that you can develop applications. You can think of developing XDP load balancers and DDoS mitigations. You can put a countdown packets from a particular IP, and you can put the logic like that. Now, if the packet counter, if the packet is coming from the same IP for a certain number of times, then you can completely drop off the packets even before the packet is received, going to be processed by the kernel. So definitely that performance stuff will be more higher than the packet is getting processed by the kernel stack, because when the packet goes to the kernel, that means it is allocating memory for the packet and it's doing a lot of other stuff. So it has to initialize a lot of stuff by the kernel. So all those processes are heavier. So this is better when you are developing something, especially for all incoming packets. If you want to put place a hook on that and process your packet, place your logic and to decide whether you want to process the packet or drop the packet or redirect or whatever, depends upon the application that you are planning on. So that's all about this eBPF network programming part 1. So I'll be covering next one on LSM hook. In LSM hook, we'll be developing another application, especially on hooking one of the sockets in LSM. So that's it for this video. See you soon with the LSM hook network security eBPF part.